The topic for today is fundamental concepts of engineering mechanics. Let's start with an introduction. So first of all, engineering mechanics is the science which considers the effects of forces on rigid bodies. It is divided into two, your statics and dynamics. So statics focuses on the effect and distribution of forces on rigid bodies which are and remain at rest, while dynamics focuses on the motion of rigid bodies caused by forces acting upon them. So for our course, and we're focusing on statics. For others, and you will tackle dynamics in your next course, MEC31. Some of you won't tackle that, go straight to MEC32. Okay? But for now, we're focusing on statics. Okay, so let's talk about some concepts and definitions. First of which is your rigid body. One definition of it is it's a definite amount of matter, the parts of which are fixed in position relative to each other. Now, a simpler meaning for rigid body is that it's an idealization of a body that does not deform or change shape. However, in actual, solid particles are never rigid. They deform under the action of applied forces, and in many cases, this deformation is negligible compared to the size of the body, therefore the body may be assumed rigid. Okay? An example of that are your steel columns. They experience deformation, however, the deformation is very small compared to its entire body. That's why we can still consider steel columns as rigid. Once again, in actual, solid particles are never rigid, but for the purpose of our discussion, since deformation is negligible, we'll consider them as rigid instead. Okay? Next, force. When we talk about force, we talk about one of two things. First is the external effect of a force. Next is the internal effect of a force. External effect of a force changes or tends to change the state of motion of a body, while the internal effect of a force produces stress and deformation in the body. To illustrate the difference, let's look at the right side, your images shown. So here we have a batter hitting your baseball. If we focus on the change of trajectory or change of motion of this ball upon being hit by your baseball bat, we're concerned with its external effect. Now, if we zoom in, and if we focus on the deformation made on the ball as it was hit by your baseball bat, then we are concerned with the internal effect of your force. Okay? So from that, we can say that external effects of forces are considered in engineering mechanics, while internal effects are for strength of materials. Strength of materials is another way to call your MEC32 subject. Okay? So since we're statics of rigid bodies for mechanics, we're concerned with the external effect instead. All right? You'll talk more about internal effect in your succeeding courses. Now, the three characteristics of force are magnitude, position of its line of action, and direction. Magnitude and direction are pretty much self-explanatory, so let's focus on position of its line of action. Now, position of its line of action, or just line of action, is the path your force takes or follows. Within that, it follows the principle of transmissibility. So according to this, external effect of a force on a body is the same for all points of application along its line of action. So here are some examples. For example, here, first one, a pushing force is equal to the pulling force as long as that force is along the same line of action. Okay, even though this is at the left, the effect of this is the same as this, where the force is to the right or at the right. Another example, okay, this force applied at the base of your figure has the same effect as if it is applied at the top of your figure. And then lastly, we have three forces at the surface of your figure. This will have the same effect when the forces are applied at its point of intersection. Okay. So as long as it has the same line of action, external effect is not changed. Okay, no matter where the point of application is, no matter where it hits your object first. Now take note, this is only for external effect of a force. Internal effect of a force is definitely dependent on its point of application. Recall, internal effect is the formation, right? So looking at the top figure, if we consider this force, the deformation will happen at the left side, and this force causes this side to compress, right? However, for the figure on the right, our force is applied on the right side, the deformation will mostly happen here. And then this side will extend because of this force. This is in compression, this is in tension, or rather, this compresses, this elongates. Deformation is not the same. Okay? That's why principle of transmissibility is only for the external effect. Okay, next, let's talk about your units. We have your pound, LB for pounds, kip, this is just equal to 1,000 pounds. 1 ton is equal to 2,000 pounds, G for gram, and kg for kilogram, or rather 1,000 grams as well. Now, some of you might encounter kip and ton for the first time here. So just know that kip is just 1,000 pounds, ton is 2,000 pounds. Okay, so just keep that in mind because in some books, they still use kip and ton as their unit of measurement. Okay, so those were your concepts and definitions. The next topic would be force systems. So force system is any arrangement where two or more forces act on a body or on a group of related bodies. The following are the types of force systems. First is coplanar. Coplanar is when the lines of action of all the forces on a force system lie in one plane, hence coplanar, same plane. Next, we have collinear force systems, forces which have a common line of action, hence collinear, same line. Next, concurrent force systems, forces whose lines of action pass through a common point. For example, we had this, right? All of these forces intersect at a common point. Therefore, we can say this is a concurrent force system. Next, parallel force system, forces whose lines of actions are parallel. Pretty self-explanatory. And then lastly, non-concurrent force systems. Forces whose lines of action are neither parallel nor intersect at a common point. Now, for this force system, some of them may intersect, some of them may be parallel. However, since not all of them are concurrent nor parallel, and you can say, or we can say that it is a non-concurrent force system. Okay? So let's have a few examples of those types. First, on the left, we have a game of tug of war. People on the left apply a pulling force to the left. People on the right apply a pulling force on the right. Both forces are along this rope right here. Therefore, both forces follow the same line of action. Therefore, that is a collinear force system. Next, we have a cable crane. Okay, so you have your wires here. As you can see, these three wires intersect at this point. Therefore, each wire carries a force. Therefore, the forces also intersect at a common point. And we call that your concurrent force system. Now let's look at a bridge. Okay. So for a bridge, each member carries an internal force. Okay. So imagine cutting through the left side of your bridge. You'll see that you have your forces. Force at the top and here at the diagonal intersect. However, here at the bottom, it does not intersect with those two. Also, this force at the top is parallel to the force at the bottom, but they're not all parallel. Therefore, this is an example of non-concurrent force system. Even though some of them are parallel, some of them are connecting or intersecting, it does not mean they are either parallel or concurrent. They are non-concurrent force systems. However, if you look at the joints, joints are the intersection of your members. Therefore, it is also the intersection of your forces. Each joint is an example of a concurrent force system. Yeah? Look here, we have three forces on this joint. We have 1, 2, 3, 4, 5 forces on this joint, and they're all connecting, all intersecting. So that is an example of a concurrent force system. But if you look at a bridge as a whole, that's non-concurrent. Okay. And then lastly, we have a group of objects. In this case, This is a group of apples. If we just take the weight of these apples, okay, weight is always downward no matter the scenario. Since it's just force of gravity, always downward. As you can see, and we have these lines representing weight, and they are all parallel to each other. So this is a parallel force system. Now let's take a sketch, or what we call a free body diagram of those systems of forces. For collinear, and along the same line. Concurrent, they intersect at a point. Non-concurrent, neither parallel nor concurrent. And then lastly, your parallel force system. So this is how you draw each. And we call this your free body diagram. Okay. So let's talk about it. A free body diagram is a sketch of the isolated body, which shows only the forces acting upon the body. It is used to distinguish between action and reaction forces. The forces acting on the free body diagram are the action forces, also called applied force. The reaction forces are those exerted by the free body upon other bodies. For example, okay, let's say you have a rigid body. Any force applied to it is your applied force or action force. Okay, any force exerted on that body. And then we have reaction force, either reacting to that action or reacting to other bodies next to it. Okay? To illustrate, we have this figure. So first of all, the free body may consist of an entire assembled structure or an isolated part of it. So we have a derrick right here. By the way, a derrick is a lifting device usually found in ships or at docking facilities. So this is what that looks like. You have your weight here being carried. Okay. So as stated above, free body diagrams can either be a part or the entire structure. This is the entire structure. So one example of creating a free body diagram is selecting a point here. For example, here at point C. So this is the free body diagram at point C. This is created by considering the forces acting at point C. Now, one thing is that whenever we have lines, wires, or anything of the sort, those things carry tension force. So therefore, automatically, this carries tension. So when you draw that, it's this way. Also remember, tension forces are always away from the body. So that's why the arrows are positioned this way. And another thing is we have this pole here. This pole also has an internal force, or rather a force exerting at point C. That's why we have another arrow here denoting the force from the pole. So this is your complete free body diagram. Now we can also take a part of your derrick to create a free body diagram. In this case, they took this mast and this pole, okay, or this column and this pole. Now take note, in creating free body diagrams, we consider reaction at supports most of the time. For this derrick, the supports are as follows. We have one here, we have one at the top, we have one at the bottom. Okay? But since we're only considering this portion, we're not considering this, our supports are top and bottom. So look here, we have a support there. Therefore, there's a reaction there. This support prevents horizontal motion. And therefore, the reaction there is also horizontal. However, at the bottom, although it also prevents horizontal motion, it also carries the weight of your structure. Therefore, there's also a reaction for the weight. That's why there's a horizontal and vertical force here. Next, as I've said earlier, when we have strings, wires, ropes, there are tension forces. Hence, there's tension here and there's tension here. Okay? Tension will only show when you cut the wire. So cutting here and here, and you have your tension. That's why there's no tension here. And that's your free body diagram for these two structures. Okay? And that ends our topic for fundamental concepts of mechanical engineer or mechanics, engineering mechanics. Any questions so far? Please answer in the chat, yes or no, yes or none. Any questions so far?
None, ma'am.
Okay, since no questions, that ends our first topic.